So everybody, welcome to 7.1 and 7.2. We're going to be looking at similar triangles and how to solve similar triangles with different problems. So what you're going to be doing is you're going to either use your previous knowledge or look on the internet, and you're going to define the following. So click pause while you figure out the definition of the two following, which is congruent figures and similar figures. So you can check your answers with the following. And so here we have the congruent figures. They have the same shape and the same size. And that means that they have the same angles and the same sides. Whereas in similar figures, you have the same shape, but different sizes, which means the angles are the same, but the sides are in ratio to each other. So we're going to look at a triangle here, and we're going to talk about some of the properties of that. So I'm just going to change the line here. And so here we have two triangles, ABC, and another triangle, DEF. And we can show that those two triangles are similar with this little squiggle here. So the squiggle represent the symbol, meaning that it's similar. So we are saying here that triangle ABC is similar to triangle DEF. And notice that ABC, we go in the same order as DEF. And so this will help us when we talk about the angles, the sides, and then the area. So the corresponding angles, if we were to say which ones are equal, we can say that angle A is equal to angle D. We can also say that angle B is equal to angle E. And finally, we can also say that angle C is equal to angle F. So in similar triangles, the angles inside the triangle should always be the same. When we're talking about ratios of the side lengths, that means that this side length and this side length are not necessarily equal, but they are in proportion to each other. So for example, this triangle might be 2 times bigger than this triangle. So if we're to talk about the side lengths, we can say that AB, which is how we say side length, AB over DE, those can compare because that's the same side of the triangle compared to the same side of the other triangle. This would equal, if we were to compare now this side, we could say BC is compared to EF. And the last side, we can say that AC is compared to DF. And so notice that each time we had the first triangle on as the numerator, and we had the second triangle as the denominator. And so this one was compared to that one, and that one's compared to that one. So if we were to say that this ratio here equals K, if you did the two sides divided by each other, we can actually compare the areas of the two triangles here. So we can actually say that the area of triangle ABC over the area of triangle DEF, we can say that this can be compared by taking the ratio squared. So this can help us to determine the area of either of the triangles. So now if we wanted to look at the first example and we wanted to decide whether the triangles are similar or not, we can actually look at the comparison of the angles. So we're going to have to explain our reasoning. So what we're going to do first is we're going to compare the sides just like we did before. So if we're going to compare, let's say, the bottom parts here, this would be saying that PQ is compared to ST of the other triangle. So notice we have this top triangle here, and we have this bottom triangle. And then we could also compare that PR is compared to RT. And we could also compare that QR is compared to RS. So if we look at these and we substitute in what PQ would be, PQ is 20 and ST is 100. PR is 10 and RT is 50. So if we continue and sub these in and reduce, so I'm going to solve these and then the answers will pop up. So now as you can see, once these are all reduced, they all have a ratio of 1 over 5, which because each side is in comparison by the same ratio of 1 over 5, which this can equal K, we can say that these two triangles are similar. So therefore, triangle RPQ is similar to triangle RTS, and then you could explain, as it says here to explain your reasoning, is because the ratios between the side lengths are the same. So if we're to look at another one here, now we're actually going to solve for values. So we're going to solve for B and G. To do this, again, you want to set up your ratios between the side lengths. So for part A, if we have BC here, BC, we have to compare which side length that is compared to on this triangle. Notice here that in the triangles, the letters that are stated, if we said BC here, our side length, by looking at the triangles, we should be able to say that that's EF. And you notice the first two letters here are compared to the first two letters here. So that would be EF. That's compared to, if we went to the side here, BD. So compare BD. And if you were to look at the triangle, it looks like EG. And here, BD. And if you look at the order in this one, it's also the first one and the last one, which is EG. And so then the last one is CD is compared to FG. And so now we're just going to actually substitute in the values. So now that we've substituted the values in, we're going to look at this part first, and we're going to ignore the last part of the ratio. So if we're to look at this ratio here, the only variable that we have to solve for is the G. The G can't be in the numerator, so I'm going to take it up because we're dividing by G. When we go to the other side, we're going to multiply by G. Same with this 9 here, so this is going to be 63 equals 21G divided by 21 divided by 21. And if we solve this, we get G equals 3. So just let me switch colors here. And so if we're going to we have to solve for B. Now I'm going to look at these ones. Notice that every time I picked two, I picked the one that didn't have a letter, and I picked the one that did have a letter. And so if we're solving this, again, we're going to take this divided by 12 to the other side, and that will get the B by itself. We're going to have 21 times 12 over 9 equals B. And so for this one, B equals 28. And so we were able to solve, and again, we should have units on each of these. So they're all centimeters, and then a therefore statement. So the last part is part B here, which we have to determine the area, which we are given the area of BCD. And so when we look at this, our top triangle we have compared is triangle BCD. And so when we do this, we're going to have the area of triangle BCD compared to the area of triangle EFG, and this is going to equal K squared. And we should be able to figure out K squared because we have this here, 21 divided by 9. This is one of the ratios, which is our K. And we're also given 49. So our next equation then will be 49 divided by the area of our triangle equals 21 over 9 squared. And if we solve for this, we will get approximately 9 centimeters squared is what it would is what the area of triangle EFG. And so there, at the end, we should always have our therefore statement, which answers the question. So next, what you're going to have to do is in this word problem here, you're actually going to have to determine the width of the river. So this is what you're going to bring to class on Monday, and then we will, I'm going to be checking this, and we'll be going over some other questions on how to solve similar triangles. See you then.